What's going on, everybody? My name's Will. Nice to meet y'all. I wanted to record this video showcasing a little game that my coworker and I were making, and more focused on my contributions, because this is my video. The game's called Riftborn. We're actually hosting a demo, a very bare bones demo on the first week of June, so let's get it. But with that being said, in all seriousness, I wanted to structure this video in a way that will give some new developers some insight on what actually goes into really making a game. More importantly, in this genre, which is a bullet heaven. I'm going to talk about performance, and I'm going to talk about my contributions and how I've thought of some systems. So let's just get right into it. The main concern that we have, especially when we're making a game, is okay. This bullet heaven game needs to shove 200 enemies on the screen. 200 to 300. 300 for performance testing, but 200 comfortably. So, or even less. So the question is, okay, how do I do that? And how do I go about it? And if it's your first time, where do I find the resources? So, my aspect of it, first of all, I program the AI. I make the AI work. And I program the PCG system. I make the PCG system work. And I program the spawning system. And I make the spawning system work. Let's just talk about AI for right now. But anyway, the AI have multiple different aspects to them. Our average AI kind of has a little bit, a couple of components on it. So we have all of these components on an AI, which is okay. It works for us. It may not all work for the individual developers, but you can see we have a flow field follower component, a brain component, loot drop component, lifecycle component, a crowd member component, animation component, dissolve on death component, and flow field movement component. So you're probably like, why all these components? And each component actually plays a very crucial role into getting the AI to actually behave like AI and also performance-wise. So the first stepping stone is, how do we get 200 enemies in the game animating correctly, right? Let's just talk about animation for right now. As you've probably inferred, you can't really use a skeletal animation pipeline with this type of genre. First of all, skeletal animation does a lot of calculations. It's good for other genres, but for this genre, you don't really need to do all those calculations. You need something more efficient. You're not really using all of that processing power and all of that functionality. So what you do is you educate yourself on vertex animations. So how it works is the shader iterates over the texture and it pulls animation data from the texture. So this is Unreal Engine actually has a plugin, a vertex animated plugin that helps. Now, how it works, and specifically how I programmed it up, is this is only just one of many things, but you specify start frames and end frames. And basically, it iterates over this index and pulls that frame data from that texture and it just keeps on indexing over that frame data. So yeah, this is all that I have here. I can go into this system in a lot more detail. I have events as well that you can tie up to these vertex animations, which are really dope. You have tags. You have, that's about it, really. But the event system that I tied up to here is actually really dope. So that's the first thing, is use vertex animated textures and use the vertex animation system. But another thing is that's good, but now you have another performance concern with your draw calls. Your draw calls are getting too high because nothing is being instanced correctly. What I did is I have this crowd manager component that is an actor that you place in the scene, but it gets placed automatically because, you know, I don't want to forget to place it. And this crowd manager basically gets the materials of all the enemies and it puts them in buckets. So that way it instances them correctly and it batches them right. So that saves on draw calls. So we're drawing multiple materials in one pass instead of many different passes. So those are two considerations to keep in mind. Now, the AI system, this is a really interesting one. How do you go with AI navigation without blowing up your frames? Traditional and Unreal Engine uses this is just the regular A-star algorithm. It's a good algorithm, but using it for 100 enemies, you don't need that level of complexity. So how it works is we introduce a concept called flow fields. And flow fields are really interesting because they help us save a lot of compute power because we're not computing the actual navigation per se. We're just computing a vector, an orientation of a vector. And first of all, before I show you, this is our current performance metric for our game that I'm still debugging. You can see how everything's nice and smooth. Now, some things are here because of the gameplay abilities. You can see one of my buddy's abilities. I know what that's from. But just overall some small stuff, like we're obviously taking a small hit on the render thread because we want to have some shadows and and we want to simulate some lighting because it's a 3D game. It's not a 2D game. But that's what our performance is looking like right now. Anyway, that being said, a good navigation system is using a flow field system. Now, this is a 1K by 1K map, and if you calculate all the tiles per se for a flow field, because how a flow field works is it's basically like a grid and of tiles. Each tile has a uniform size with each other, and all the tile has in it, you can shove multiple things on a tile, but normally what a tile has in it is just a direction vector. And so the goal is to say, hey, just follow this direction vector. Now, you can take it one step further and weight these tiles, which I do. So that way the enemies, depending on where they are, they go in a sensible direction. And that's a whole different algorithm. But you're probably like, oh, that's pretty cool. I'll go with the flow field. Well, first thing is if you simulate a 1K by 1K flow field, that's going to take a little bit of compute power. And if you only have a couple enemies in the scene, like 2 enemies or 100, and they all follow the player in like a certain area, you're wasting all of that area that no enemies are on. So what we do is we generate a hierarchical structure, so hierarchical flow fields. And how it works is these grids, they're basically how do I say this? They're like built in regions. And so region is let me go into here. A region is considered X tiles wide by X tiles, you know, in the Z direction if you're in Unity, Y direction. So X by Y. And you generate a little region right here. If I show you, because I have the debugger up, I'm assuming this will really only show if I actually simulate the game. And so you'll actually be able to see everything here. So I have the show regions. So because my material is crap, you won't really be able to see anything. But here's what's basically happening. This region is being calculated right here, which is really dope. And you'll see that these are the direction vectors. So you can see how all of the vectors kind of point in the same direction. And the enemies, they just look at, okay, what tile am I on and what's the direction vector? Boom. Now, one problem is, if the player moves too quick, this region becomes stale. And the enemies stop because they have no vector. Way around that is you stamp ghost regions. So the old fields, they're promoted as a snapshot, a ghost snapshot, and these agents will only fall back to this ghost. Everything is built asynchronously, which is good because you don't want all this happening at one time because it's a lot of calculations. So that's the flow field system in a nutshell. Next, I've already talked about the animations and I've already talked about the flow fields, which is good. Let's just talk about the spawning system. So the spawning system is more like a polling system. It's not really a spawning system, but it looks like it's a spawning system. So I'm just going to roll with the spawning system. In a game like this, you really want to avoid spawning enemies very frequently. That's a lot of allocation space. And so you're going to get frame hitches. So what you do is that you spawn enemies during load, and you shove them in a pool. And when it comes time to use the enemies, they're flip their state to alive, and it just basically positions them at a certain spawner and toggles their pipeline. And when they die, they get pulled and they get inactive. And so you're just resetting over and over and over again. So that is that at the end of the day. Also, a cool thing with the spawning system is if you look closely, I'm going to remove that debugger, you'll be able to see, if I do it right, you'll be able to see these spawners. So you see these spawners. That's a spawner, that's a spawner, that's a spawner, and this is a spawner right here. These spawners obviously are not in a circular direction. What they are is I stamp the camera's frustum to the ground so I get this trapezoid shape, and then I position these spawners at an offset from this frustum. So that allows the spawners to actually be really close to the viewport instead of, you know, at the same radius, because the frustum is different. It's not a consistent area all across, so you can't really use a radius. The interesting thing that I do here is I take the player's forward vector followed by his velocity direction, and I take a dot product of that. And what I do is, in this spawning system, I actually split it up into slices. So picture this as a pie, and each, I have it as like 16 slices. So each little distance is a slice. And so what we do is we get that orientation of the player and where he's going. So if I'm going over here, we get a dot product of like, let's just say 0.5, right? And so next thing you know, I'll bias these spawners a lot more, so it feels like the enemies are coming around the player. So wherever the player goes, the enemy goes. And that's how you do something like that. So, yeah. But now, the last conversation that I want to have, well, actually, one thing that I didn't talk about is when you're building a flow field system or enemies, you need to make sure that you control your ticking and also make sure that you're really cognizant of the tick groups. If you can make everything in consistent tick groups, that helps a lot. But in terms of ticking, the best thing that you can do is put some sort of LOD mechanism in there for ticking. So that way it doesn't tick consistently. If the enemies are outside of the frustum, you disable their mesh, and you also turn down their ticking to like, I don't know, 1.5 hertz, right? And when they're really close, you pull them to like 20 hertz. Reduce is like 5 hertz or something like that. And so this helps take a lot of the pressure off the CPU. In terms of the flow fields with obstacle avoidance as well, during your flow field, you compute the direction vectors, but also you need some way to see, hey, look, is an obstacle here. So while the flow field is being built, which is during load, and any of the static obstacles we have, we actually do line traces. And any tile that's really on that mesh is considered a dead tile. And so it has a very strong repulsion radius on it, which allows the enemies not to get or to collide on it. Another thing too is with all of these enemies, how do you focus on separating them? Because collision is a very big issue. I'm just going to be brief. Use a spatial hash. Do not focus on them generating collision events because it will not work out. You do not want these enemies generating collision events. They can receive collision events, but do not let them generate collision events. So that's a very important thing. So last thing that I also want to talk on too is performance and Unreal Engine with performance. I'm just going to be very brief. I will say, okay, this does relate. The more general a game engine is, the worse it will be with performance. When you're making a game engine, you normally make a game engine for really one type of game. So that's because you can optimize your systems in a certain manner. Like first person's kind of different from third person. So with that being said, Unreal Engine is a very general game engine. They have all these features, and yes, it will not be an engine that is optimized for a certain game in terms of performance, but the state that Unreal Engine is in is actually very good. Um, they've done a really good job with making Unreal Engine run really well, making you have the ability to diagnose your performance and also the ability to make performant games. The reason why a lot of games using Unreal Engine are not performant is most due to the fact that game developers don't know how to optimize. They don't know certain systems exist, and they're not really cognizant of any better approach. They want to use the latest and greatest features. Nanite, Lumen. Nanite's okay. In my experience, I hadn't really had that much luck with Lumen. I just use screen space, but it's a give and a take relationship. As I just explained with all of these systems, these are systems that are not really known as much as like the conventional approach, like Unreal Engine's built-in navigation system or the skeletal animation system. And so if you make a game like that, you'll be under the assumption that Unreal Engine's crap for performance. So it's just learning how to use the existing tools that the engine gives you and also thinking outside the box a tiny bit that will ensure performance. Because I just showed you our trace data, which is like this, right? And so for a, for a development run, this isn't even packaged, by the way. It's actually really consistent. You can see, yeah, we have some spikes here, but this isn't from me. That's from my buddy. I'm just joshing. Understanding how to use Unreal Engine sites and Unreal Engine's diagnostic tools, like the stat tools, and also the GPU tools, will help you a lot because this profiler here is really good. And it will tell you what's going on. Like, if you're looking here, it's like, okay, in my render thread, I'm kind of spending some time here on shading and lighting. So that would make sense because we do consider shadows, and our lighting right now is kind of crap. I haven't optimized for lighting because we don't have the correct assets yet. And so with that being said, you can see, okay, let me just look at the GPU real quick. Oh, wow, I'm spending 1.5 milliseconds on shadow depths. So there's two ways that you can go about it is, okay, yeah, just disable shadow depths entirely, but we don't want to do that. Or we can turn back the quality, the resolution of our shadows, which that's what we have to do. So yeah, that's that. And you can still see how Slate is messing with us a little bit. So Slate's taken off 1.5 milliseconds. But overall, this is what you want to strive towards: is a nice, consistent, performant graph. It's okay if there's a few hitches in there. You go, make a build, do it again, and do it again. But in other terms, I mean, I've optimized one of our past projects. That's an open world. And it's just learning the nice little tips and tricks that go about it. You can see I have some animation stuff here, which I can probably improve on. My performance-wise is in my ticking. I've done the best that I can do for the ticking because I still need to keep in mind the obstacles and still need to keep in mind the landscape as well. One thing that's actually really cool, and I've came to this conclusion, I don't know if other people have used it, but when you're in a 3D game and you're using a flow field, instead of, using, you don't want to use the traditional character movement component. That's also a big no-no. You want to make your own movement component, and you don't want to tie it to the character movement pipeline. One interesting thing is to consider a height field if you have a lot of tough terrain, um, and have him simulate the height field's Z position at that specific point. It will work very well than considering, than turning on, physics. That is a nice little crack right there. But yeah, that is our game right now, and I guess I should just play it. Let me just give it a quick play. Let's tear down this. Oh no. Oh no. I got disconnected because I was outside the character. And so now I gotta start it again like an idiot. Okay. So, how our game looks right now is, the one thing that we have to do is we have to pre-compile the shaders, because you'll always see we get a nice little hitch. Apparently we didn't get it that time. But this is what goes into making a game like this, that you have to consider all these different enemies types. They move differently too, by the way, and they also switch differently. So like the plant monsters, if you get close to them, they'll actually turn melee. And then, if you get far away from them, they'll be ranged again. So you have to consider all of that. Each enemy has their own little unique quirk. Like spiders are annoying as hell, and all of that jazz. So yeah, that is that at the end of the day, really. It's going to be a really fun game to play. My buddy's got the sword, and I don't got the sword because I don't know how to use the game yet. But we have this ultimate ability, which is really cool. And yeah, I like the ultimate ability. The ultimate ability is dope. We have a wall. And you can see also here that I have dynamic obstacles, which was kind of interesting to attempt. Because previously my obstacle avoidance was only static. But you could see how the enemies, they actually go around the walls. And how I'm doing the walls is when the wall comes down, I do a bunch of traces, and I flip those tiles to be repulsive. Only for the life cycle of the actor, though. So I have this component that's attached to the actor, and I do everything through the component. So when the component dies, it says, hey, unregister. But yeah, if you see, if I head this way, you can see the enemies starting to come in to play. So that is that spawning dot product in effect. And the strength of that can actually be controlled. So obviously I'm dead, which is good because that means that the enemies are actually hitting me. So how the spawning actually works, if I were to go into a little bit of detail, which is, this is going to be really cool. I actually got to go down to here. So inside of our level, I've streamlined a lot of stuff, but the only three things that really matter is the level spawn data, the progression band data, and the spawner config. Let's look at the level spawn data first, because this is actually kind of what's tied to the level. This is like the rules. So, in a nutshell, basically, this level data says, hey, these enemies are allowed to spawn in this level. If this spawn definition is not there, this enemy, no matter where you define it, will not be able to spawn in this level. Then, the next thing is, my partner wanted the ability to also define constraints on what enemies can be present in certain biomes. So you can see here that I only have one biome in right now, but I want these enemies to spawn or have the ability to spawn in when I'm in the forest biome. And if I'm in the crimson biome, for example, only this enemy will spawn. So that's something there. Then what we do is, I'm going to save the best for last, but going over to this spawner config. So this is the spawner that is around the player. The spawner holds a pool. The spawner spawns at a certain interval. The spawner can also burst spawn. The spawner has 8 sectors. And it also has a density sample radius, which I actually didn't talk about. But if you remember the analogy of with the pie, each slice will have a density. And the density is calculated from the amount of enemies within that slice. So it would not make sense to spawn another enemy within a very dense slice. So that is how that kicks into weight, and especially with the scoring as well. The pool has a burst, so that way the enemies can really come at the player. Spawning sectors have certain cooldowns. So yeah, really. And what I did is that I made a higher abstraction. So instead of a dot product parameter, I call it the escape cone width, which is just the amount of cones that get activated, if the player is trying to escape. So it's how many spawners get activated in that direction. So that is that. And then the progression band. This is actually the meat and the grease. So this progression band obviously isn't the polished version of the progression band, but if I were to go to the polished version of the progression band, something that will be in the game level, not just for shits and giggles. Our typical progression band kind of looks something like this. So how it works is we basically take the player's level and we band it. So right now this accounts for players level 1 to 30. And so what we do is we split that up into bands, each with its own width of 5. So levels 1 to 5, 6 to 10, 11 to 15, 16 to 20, 21 to 25, and then 26 to 30. So that is our progression mechanic. And so what we do is that, these base points, each enemy has an amount of points that it costs to spawn. And so basically this will actually prioritize the enemies with the least amount of points. And this is how many enemies are present in this band. So only one type of enemy is present in this band. Co-op settings. This is obviously, as my partner said, we account for multiplayer, but we're not super focused on it. But this actually works though. If you're playing with 2 people, the system rewards you for being closer together in a group. If you stray away, you will encounter more enemies, and that is with this spawn rate multi if you're split. Pressure settings is basically we have this target amount of enemies that we need to be at, but if we have summoners and etc., then we need to adhere to this max enemies. So also we have here is a ramp duration curve. So this basically doesn't allow all of the target enemies to be active at once. It kind of ramps up slowly. So yeah, that is the whole shebang. And that is a little bit of a glimpse of what goes into making a good game like this. I hope you guys enjoyed. I know that you had to listen to me talk a little bit, but hopefully if there's any developers out there hopefully some of them found this talk a little bit insightful. So until next time, peace.